Am I audible to people online before I start? All right, thanks. Okay, just a reminder about test number 3 tomorrow. Okay, I know it's a short week, so the days are a little bit off. Okay, tomorrow it covers chapter 3. Just I hope all of you got a chance to do the homework in 3.3 and 3.4. Okay. Just a quick checklist of things that you should be knowing for test number 3. Mostly about algebraic skills. It's not like chapter 2 where you have to keep track of YP and YH and all that. So the list is mostly about what you should be knowing in terms of algebra. You need to know how to complete squares. That is, if you cannot factor a quadratic expression, then plan B is to complete the squares. Okay. You should know how to do partial fractions on 3 kinds of cases. Okay. So case 1, if you have a bunch of linear terms in the denominator, so something like, I don't know, difficult to make up these things. So let's say k over s minus a times s plus b times s minus c. So for example, if we have say 4 linear terms in the denominator, that would be a over s minus a. Sorry for picking the same letters, but this is uppercase as lowercase. So it's b over s minus b plus c over s minus c. And plus d over s plus d. Okay. All of you know how to do it. Okay, these are the cases that we have seen in most of the examples. That's case number A. If you have a repeated factor, just be careful. So if you have, say, s minus a whole square times s minus b, the repeated factor must be done as many times as you have in this exponent here. Okay, so a over s minus a plus b over, it's not bs plus c, okay, it's b over s minus a whole square plus c over s minus b. Okay. So you don't treat this as a quadratic expression and do bs plus c, it's just a linear term. If you have a quadratic, well, I'm keeping the numerator as k just because I'm not being very creative about what could be there. Okay, but that could be anything which is of not a higher degree than the denominator. Okay, so if you have, say, s plus a times s squared plus bs plus c, okay, so that's a term in degree 2. So for example, if you have s squared plus 4 or s squared plus 9, that is usually what you see in your problems. Okay, but the worst possible case is you have s squared plus bs plus c. Then you have a over s plus a plus bs plus c over s squared. Just to remind you that if you have a quadratic term here, not a repeated factor, okay, degree 2 term here, that must be of degree 1. Please don't make that mistake. Okay. So those are the 3 partial fraction cases that you'll be seeing. Most of the examples you have done in class and in the homework. Okay, you don't see anything outside of these. In terms of the initial value problems, the most important things are the ones concerning the Heaviside function. Its Laplace transform is, I hope all of you have gotten used to this by now. Okay, this is case number 11, e to the power of negative as over s. And the second shifting theorem, please observe the subtle there's some unexpected thing that you see when you write this down, right? And it's okay to be a little bit shocked when you see it. Okay, you would expect that you would just multiply the Laplace of this with this. It's not what it is. Okay, we derived this, and this is the second shifting theorem, not you do this one, you might end up doing a lot of unnecessary dirty work and also get the wrong answer. So not this one, it's this one. Okay. And this is what we call as a second shifting theorem. And it's in your Laplace table. You don't have to memorize this or anything. Okay. So some of the common mistakes on past exams and quizzes is that students would put an S there even if the table does not have it, and then it leads to this unnecessarily complicated partial fraction after that. Okay. And also when you shift it backwards, L inverse of e to the power of negative as times f of s. Don't forget to shift this by a. I know it takes a little bit of getting used to. So this is a hint. Okay, so e becomes u whenever you have this term multiplying this Laplace transform, you need to shift your output by a. Okay. And yesterday we saw the last of these weird creatures. Okay. Being either 0 or infinity. This is for t not equal to a, and this is for equal to a. Okay. In reality, that infinity is just some finite amount of force that you're applying at an instant time. So this is a impulse or instant input. And this is a step input. Okay. And we saw that they are kind of related in a derivative kind of way yesterday, okay, but not in a traditional calculus way. It's a more mysterious relationship there. But either way, the Laplace transform of the Dirac delta function Dirac delta, and this is the Heaviside step function. Okay. And that's just equal to e to the power of negative as. The difference between these two is the absence of s in the denominator here. Okay, so there are places where s is in the denominator, and there is these two where s is not in the denominator. Be careful about these small things. So these are the main items, okay, which you will be using at one place or the other on tomorrow's test. So just be mindful about all these things. Is there anything that you want me to go over in this list? Any examples or any homework questions or? So here are some, I don't know if you want to write this down, but some common mistakes on Laplace transform problems. Okay. One is the wrong partial fraction setup. Unfortunately, these are big mistakes because it changes the complexion of the solution significantly. So second one, which is unfortunately a really bad one, is trying to complete the squares. Trying to complete squares when you can factor it. That kind of pushes you to a corner where you don't know what to do, and then you start inventing your own rules of partial or Laplace transforms, and the solution gets wrong from that point. Okay. So that is another common mistake. The third one is confusing the two functions that I wrote up there. Okay. Mistaking u for delta and delta for u. You just need to look at it carefully. I mean, it should be pretty clear. It's a printed exam, so there is no reason to be confused between the u and the delta functions. Smaller mistakes are forgetting to shift terms where there's a second shifting theorem. Okay. I think those are the relatively smaller mistakes. If you survive the first three things without making any huge mistakes, you shouldn't be copying the problem wrong to make it easier than what it's supposed to be. Okay. So the problems are written for testing your certain things. So if if it is given as y double prime minus 5 y prime plus 6y equal to something, okay, you shouldn't be copying it as y prime minus 5 and say that, oh, I just missed a prime there, so it's suddenly a first order equation. So don't just copy it correctly, take your time, okay, because I know it's a small error in copying, but it changes the problem altogether. All right, so those are the tips for Laplace transform. I know it's a slightly complicated topic, so just go through all the examples we did in class. Okay, I won't ask you anything beyond that, but make sure that you have a nice list of notes or formulas in front of you. Don't try to be distracted. Okay. All right, any questions before again, I'm open to doing any homework questions or examples that you want either today or tomorrow. Okay, just bring it in and I can do it. Any questions here? All right, then let's move on to chapter 4. Okay. So it's a little bit of an awkward transition because you're going from differential equations to linear algebra. It might seem like a very abrupt change, okay, to seemingly two different fields of math, but we're trying to somehow merge it together at some point. Okay. So the first few lectures might seem a little bit rough because of the totally different appearance of things. So we're going to say goodbye to calculus and differential equations for a while. Okay. And some of you may have taken some linear algebra in the past, so please bear with me if I'm a little slow the first few lectures, trying to bring everybody on the same page here. All right, so chapter 4. This is the linear algebra part of the course. If you've never taken linear algebra, okay, it's a part of math that deals with either systems of linear equations, which is what it's mostly famous for. Okay. Those of you who really take a formal course in linear algebra also know that it's about linear transformations. Okay. That is where all the beauty of linear algebra lies. The first one is kind of the bare bones things, okay. Systems of linear equations, which all of you have been doing that throughout your life. Okay. The second one is where it finds all the applications, especially in computer graphics and data analysis and all that, linear transformations. That's a big thing. Okay. Our focus will be mostly on this. If you want to do this one, you should take the actual linear algebra, which is math 2331. Okay, that goes into actual depth of all the concepts that we'll be doing. So this part will be mostly computational for us. I won't be proving any theorems here. Okay, if you are dying to see proofs of theorems, you should take this one. Okay. So section 4.1 is about the basics of matrices. A lot of people think that linear algebra is a study of matrices. It's not. Okay. Matrix is just one of the tools that is used, but that is just a part of it. Okay. So I don't want you to think that this is what linear algebra is about, but we'll be mostly living with matrices for the next couple of weeks. But when you talk about systems of linear equations, let me just tell you some basics. And all of you know this, if you have two equations like this, x plus y equal to 3 and 2x plus 3y equal to 5. Okay, there's two equations and two variables. Now you don't need a advanced degree in math to solve this one. Okay, you have done this in middle school. You know how to solve this. So these are two straight lines in xy plane. Okay. And they intersect at one point, hopefully. That is your unique solution. The two straight lines, if they intersect, will always intersect at a point. Yeah. The question is, will they intersect or not? Okay, that is what linear algebra mostly tries to explore. Is the solution always guaranteed? And if it is there, is it unique or not? Okay. So this is the best possible scenario. You solve a problem, you have one solution, and you move on. Okay. Now, life will be boring if all the problems that we solved had just one solution, and we always knew that there was a correct answer. The interesting part of linear algebra comes with cases which don't have unique solutions. Okay. So we'll be spending very little time with those kinds of systems. So what we are mostly interested in would be things like this. So I'm writing another system here, okay, so which means anything that solves must solve the first equation and the second equation at the same time. And I think if you just look at it carefully, you know something is not right about it. I took x plus y equal to 3, and then I multiplied that equation by 2, but maybe I forgot my multiplication or whatever reason I got a 5 here. Okay, this does not have a solution. Okay. These are two straight lines which are going parallel to each other. So there is no solution to the system. It's called an inconsistent system. Okay. The reason it's inconsistent is because I should have done 2x plus 2y equal to 2 times 3, 6. Instead I did 2 times 3 equal to 5, which is not right. Okay, so that's inconsistent. What about this one? X plus y equal to 3 and 2x plus 2y equal to 6. Now I got my multiplication correct. Okay. How many solutions does this system have? Okay. Infinitely many, right? This is just the same straight line here. Okay. This has got infinitely many solutions. So no matter how many variables and how many equations we have, okay, these are the three possible scenarios we need to expect in linear algebra all the time. Either it'll have a unique solution, which nobody cares for, at least for our theoretical purposes. Okay. I'm not saying that nobody cares for that, but that's boring, because you can use MATLAB or something and get that. The case with no solution is interesting because we need to avoid this one. Okay. The case which comes with a lot of information that is useful for us is this one. Okay. I know it's surprising. Why is this useful and not that one? Okay. We'll see this. Why? So the good news is that even if you had 100 variables and 1,000 equations, these are the only three situations that will ever arise in linear algebra. Okay, so irrespective of the number of equations slash variables, because in real life applications, it's not going to be a two variable, two equation problem. It might be 375 variables and 500 equations. Okay. So no matter how big the system is, these are the only three possible cases of solution that's ever going to happen. Okay. Only three possible outcomes. And we're going to deal this from a computational point of view, as I said. Okay, our objective is to see how this is somehow related to study of differential equations. So the concept or the notation of a matrix is just a tool to understand this process. Okay, it's not the beginning and end of linear algebra. It's just part of it. Okay. So let's get back on track now. Let's look at what a matrix is and some types of matrices and how you operate on matrices and so on. Okay. So the whole company of MATLAB is built on this process of matrix operation. So basics of matrices, section 4.1. A matrix is the plural is matrices, singular is matrix. Okay. So matrix is a rectangular array or it's an arrangement. Okay. So that's why it's a favorite tool for people who do coding and computational things, because you can store your information in precise points, okay, very efficiently. Instead of defining 1,000 variables, you can just define arrays. So matrix is a rectangular array of numbers or variables, I don't care. So they're called elements. So numbers or variables, whatever they are. Okay. Element of that represents a set of data. So we need to first get used to some convention here. Okay. So usually a matrix is defined in terms of how many rows and how many columns there are. So M by N matrix. So it's written as M times N, but it's read as M by N. Okay. Well, if you call it M times N, I don't care, but the usual language is M by N. A matrix is a matrix with M rows and N columns. So that's a lot of writing. Let me make myself very clear so that we all talk the same language here. Okay. Rows are going from left to right, columns are going vertically from top to bottom. Okay. We shouldn't have any confusion. We shouldn't call, oh, I want to call this as a column and that as a row. We can't do that. Okay. So a row goes from left to right, because we don't want our communication to break down here. Okay. Columns going from top to bottom, bottom to top. Okay. So you don't have to say 5 rows by 3 columns. Just say 5 by 3. It means there are 5 rows and 3 columns. Okay. So a 3 by 2 matrix will look like this. 2, 3, 5, bit too many. 2, 3, 5, 2, 1, 4. Okay, they don't have to be all positive. You could put negative there, maybe put a fraction there, okay, maybe put a decimal in there, maybe put an irrational number in there. So all kinds of weird things can pop in there. Okay, but the size of the matrix, also called the dimension of the matrix, is specified by rows first, column second. Some textbooks call it as the size of the matrix, some call it as the dimension of the matrix. Okay. And if you look at each column, which are the vertical parts of this matrix, okay, they are actually representing vectors if you have taken calculus 3 ever, right? Those are just written vertically down. Okay. So if the number of rows and columns are the same, we call it as a square matrix for obvious reasons. We call it a square . So a 5 by 5 matrix will have 5 rows and 5 columns. That's a square matrix. Most of our calculations in our course would be with square matrices because they're convenient. Okay. Occasionally, we might get into non-square matrices. So 3 by 3 matrix will look like this: 1, 2, -3, 4, 5, 6, 7, 8, 10. Okay, that is a square matrix, obviously. Okay, it looks nice because both from top to bottom and vertically, and from left to right, they kind of look nice and uniform. So if A, we usually use uppercase letters to denote matrices. Okay, so if A is I haven't figured out if it is an m by n matrix or a m by n matrix. What do you think? What should be the article there? Does it matter, or is it like a mathematical thing which nobody thought about? I don't know. If A is an m by n matrix, I know it sounds very weird when you write that. Yeah. Okay. If A is an m by n matrix, then we define its transpose so the transpose is denoted by A with a superscript T. Okay, I'm not going to call it A to the power of T. Okay. Just a notation. So T for transpose. So if A is an m by n matrix and AT, which is the transpose of A, is an n by m matrix, obtained by swapping the rows and columns of A. So whatever rows you had in the matrix A will become columns and vice versa. So if A is the following matrix, say 1, 2, 3, 4, 5, 6, 7, 9. Okay. Let me see if you understand what I'm trying to say here. What is the dimension of this matrix? 4 by 2. Good. Okay. Then A transpose would be a 2 by 4 matrix. Okay, so the columns will become rows, the rows will become columns. So the first column would be the first row here, 1, 3, 5, 7. And the second column would be the second row here, 2, 4, 6, 9. Okay, so this is a 4 by 2 matrix. This is a 2 by 4 matrix. we won't deal with the concept of transpose a lot in this course, but it's useful to know these, since you're doing some linear algebra here anyway. Why don't we just deal with all these lingos, Suppose A is a square matrix. Once again, that means it has the same number of rows and columns, okay, say n by n. And if the matrix is equal to its transpose, okay, you cannot have a non-square matrix equal to its transpose because they are different size, okay, they cannot be equal. So it has to be a square matrix in the first place, and if the matrix is equal to its transpose, then A is called a symmetric matrix. Because of its symmetric appearance, that is why we call it as a symmetric matrix. So an example would be A equal to 1, 2, 3, 3, 4, 5, 1, 2, 3, and I should adjust this now, 2, 3, 2, 3, 1, 2, 3, 2, 4, 6, 2, 4, 6. It's always a challenge to bring up these examples. So the first row here is the same as first column, the second row is same as second column, third row is the same as the third column, okay. So even if you transpose this, well, you're just writing the same matrix, okay. 1, 2, 3, 2, 4, 6, and 3, 6, 5. That is what is called as a symmetric matrix. Any questions about any of these? I know I'm just listing a lot of definitions, okay, most of which are pretty obvious when you look at it. Oh, it looks symmetric, so okay, so the word is appropriate. Okay. Now, suppose A is a square matrix. Okay. And if all the elements below the main diagonal the keyword is below, okay, the main diagonal are equal to 0, that's a great matrix from a computational point of view. Okay, you kind of took care of a lot of things and brought in a lot of zeros. Okay, your computation has become a lot more easier. Such a matrix is called an upper triangular matrix. Called an upper triangular matrix. One problem with this definition is that it does not say anything about what is above the main diagonal. Okay, and that is for good reason. We don't care what they are. The only requirement is that everything below the main diagonal should be equal to 0. Okay, there is no restriction on what is above the main diagonal. They could be equal to 0, maybe not equal to 0. Nobody cares. Okay. So this is a 3 by 3 upper triangular matrix, for example, 4, 5, 7, 0, 0, 0. Okay. This is the main diagonal for the matrix. Okay. The main one goes from left to right, okay, along the diagonal like this. So this is the main diagonal. And if everything below that is equal to 0, okay, without caring for what is above it, this is what we call as an upper triangular matrix. So this is a 3 by 3 UT upper triangular. Okay. So similarly, you can talk about a square matrix where the entries which are above the main diagonal are equal to 0. Okay, that will be a lower triangular matrix. So similarly, for any n by n matrix A, okay, all these are only applicable to square matrices because only then we can really define a main diagonal. Okay. Any n by n matrix A, if all the entries above the main diagonal are equal to 0, then it's a lower triangular matrix. Lower triangular matrix. So a lower triangular 4 by 4 matrix will look like this. So 1, 0, 0, 0, 2, 1, 0, 0, 3, 2, 5, 0. Trying to make sure that everything there is 0. Okay. Did I get that right? Again, we don't care what is on the diagonal. Okay, that could be 0 or non-zero. What I need to preserve is this triangular part here. So this is the main diagonal. Everything above it is 0. It's a lower triangular matrix. So when somebody says, I have a triangular matrix, it could be upper or lower triangular. Okay, you have to be clear about which part is equal to 0 or not. Now, if all the entries above and below the diagonal are 0, okay. So if A is a square matrix, in size n by n, and if all the entries above and below so the only possible non-zero part now is the main diagonal, okay, which also could be 0, but let's keep that non-zero. So all the entries above and below the main diagonal are equal to 0. We call it as a diagonal matrix. Okay. Not a very creative name. Just says that the main diagonal is the only thing that is non-zero. So that is easy to write. 1, 0, 0, 0, 2, 0, 0, 0, 3 is a 3 by 3 diagonal matrix. It's both upper triangular and lower triangular. Okay. Both upper and lower triangular. And that's what I mentioned earlier. There is no restriction on the other side of the upper or lower triangular. They could be 0, even then they qualify to be upper and lower triangular matrix. What if these numbers were also equal to 0? What do you call that matrix? 0 matrix. So you don't have to be very creative with these names. Okay. And the zero matrix is a diagonal matrix, upper triangular and a lower triangular matrix. Okay. The only problem is it's not useful for anything. So I don't know if you should write that or something, but so if all entries are equal to 0, we have a zero matrix. You still have to write all the rows and columns. You cannot just write a number 0 and say it's a zero matrix. Okay. If there are 100 rows full of zeros, you have to write all the 100 rows. And this is diagonal, upper triangular, and the lower triangular matrix. But there is one diagonal matrix which is very special, okay, which we'll be making use of a lot during this course. If all the diagonal elements are 1, still a square matrix, and it's a diagonal matrix. Okay, so if A is a square matrix, square diagonal matrix, which automatically means that everything below and above the main diagonal are equal to 0. Okay, so if A is a square diagonal matrix with all the main diagonal elements I keep on saying main diagonal because there is also an off diagonal which nobody cares about, but I don't want you to go there. Okay, main diagonal is the one that goes from the upper left corner to the bottom right corner. Okay, so with all the main diagonal elements equal to 1, what would we call that matrix? This is the most important square matrix for us. Okay. Any guess about what we would call this matrix? Yeah. One diagonal. All right, well, that's not a bad one. So we call it as an identity matrix. Okay. And we'll see why it is called identity matrix soon. Identity matrix. So for this course, okay, even if you don't know what an upper triangular matrix is, lower triangular matrix is, this one you should know. So a 2 by 2 diagonal matrix looks like this: 1, 0, 0, 1. A 3 by 3 identity matrix looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. And usually we use the uppercase I for identity. So this is identity 2 by 2. This is identity 3 by 3. You might think, what's the big deal with this matrix? Okay, why is this important and why is that not important? Okay. If you look at these columns here, and if you have taken calculus 3, and if you have not taken, it's okay. Those are nothing but your unit vectors along the x and the y axis. We will come back to this again later. Okay. This is where linear algebra kind of creeps into other things of mathematics. Okay. These are the unit vectors along the x and the y axis, which you call as I and j in physics. Okay. So geometrically, it has some significance at this point. It's not a random set of things happening there. And similarly, this one, those are the unit vectors along the x, y, and z axis in your R3. Okay. This is your x axis, that's a y axis, z axis. This is the unit vector along the x axis. We call it as I usually. Okay. This is the unit vector along the j axis or the y axis. This is your 0, 1, 0, because x is 0, z is 0, y is 1. Okay. And this is the unit vector k along the z axis. So one of the reasons why it is so important is because they will help us later in preserving the identity of certain things. Okay, that's why it's called the identity matrix. So things which are being transformed using these matrices, they won't change their position. Okay, they're going to stay where they are, and that's why these matrices are super important. So even if you kind of blank through the other parts of today's lecture, okay, please take note of this one. So of course, it's a symmetric matrix, it's an upper triangular matrix, a lower triangular matrix, and it's a diagonal matrix. Okay, all kinds of things. And this matrix will be our leader at some point next week and will be dominating a lot of our calculations. But before we reach there, we need to get used to some matrix operations. Any questions up to there? Any questions about any of the definitions or terminologies or any? I'm just assuming that nobody has ever seen this before. So if you have seen this before and thinking, oh, this guy is so slow, just bear with me. All right, addition and subtraction of matrices. I hope all of you know that addition and subtraction are the same operation. Okay. Two matrices A and B. Can be added / subtracted. Okay. If and only if what do you think should be the remaining part of the statement? If and only if, yes, they have the same dimension. Okay. They don't have to be square, they have the same dimension. Makes sense because what we're going to do is just add and subtract the entries at the corresponding positions, so they better match up with their size. Okay, so they're the same size or dimension. When you do this, that's when people think, oh, linear algebra is so easy because all you're doing is adding numbers. So when I say same size or dimension, there must be m rows and n columns, whatever m and n are. And the sum a plus b or the difference a minus b is also an m by n matrix. Okay. You shouldn't start with two matrices and get a number out of it. So they should give the same creature when you add those two or subtract those two. It's also an m by n matrix whose entries are the corresponding entries added or subtracted together. So we'll have some fun with this, adding and subtracting numbers. That sounds like fun. So let's say a equal to 3, -2, 5, 4, 4, 1, 2, 3. B equal to 1, 2, 3, 4, 5, 6. Can we add them together? No. 7, 8. Now let's find a plus b and a minus b. You know, one day you're learning about Paul Dirac's function and next day you're adding numbers. Okay. I'm not going to ask you what a plus b is. Okay, so I hope all of you understand when I say going to add and subtract the corresponding entries. So The first entry would be 3 plus 1, 4. Just correct me if I'm getting this wrong. 0, 8, 11, 8, 6, 8, 11. That's right. A minus B. This is a tricky one, right? 2, -4, 2, -3. And 0, -4, -4, -5. Did I get those right? How many more examples do you want about this one? Another 5 or 6 more, or how about fill the next test with 5 of these questions? Advanced level math, right? Okay. So that's the story with adding and subtracting matrices. Okay. Similarly, you could multiply a matrix with a scalar. That is also a very short story. So if k is a scalar, preferably not equal to 0, okay. The scalar means a constant, then k times the matrix A will scale each entry by k. Okay. That's why it's called a scalar. It scales things. Okay, so if we take the same matrix A and you do 3 times or -3 times A, it's going to be -9, 6, -15, and -12, -12, -3, -6, and -9. So there is nothing mysterious about matrix addition and scalar multiplication. So if you look at some of the first set of homework questions in 4.1, it'll ask you to find 2a minus 3b, 4a plus 5b, and so on. Okay, so those are just exercises to help you relax during stressful summer. Okay, now the next one you should be careful. Okay, multiplying two matrices. I've seen students who try to kind of sneak their way out of this process. Okay. For some reason, some students, they refuse to learn this, so I don't know why. It's not the same as adding and subtracting matrices, so it's a little bit confusing at first. So multiplication of matrices. If you've not seen this, be careful. Okay. A completely different type of operation here. It's not a very intuitive operation like addition and subtraction. Two matrices A and B are compatible for multiplication to give the product AB. Okay. I'm being very careful about what I'm writing. Okay. So if two matrices A and B are compatible for multiplication to give the product AB, if and only if the number of columns in A is the same as the number of rows in B. Okay. That's a strange requirement. You will see pretty soon that it makes a difference whether you write AB or BA, okay, because it matters which one you write first. It's the number of rows in the first matrix. This is called the multiplicand. Okay. and this is called the multiplier. So if you switch those two, then you have to check this requirement for those two again. The number of columns in the multiplicand must be equal to the number of rows in the multiplier. So this the first matrix is always the multiplicand, and the second one is always the multiplier. So in terms of notations, okay, if A is a m by n matrix, the requirement is that the number of columns of the first matrix must be equal to the number of rows here. Okay, these must match. That is a requirement. We don't care what is on this side. Okay, this number is any arbitrary number. This number is any arbitrary number. These two things here, the number of columns in A must be equal to the number of rows in B. Okay, these must be the same. So if you take these two matrices and try to do B times A, that may not be even possible. Okay. And the way two matrices multiply is a row versus column operation. Okay. It's not corresponding elements multiplying each other. I wish that was the case. It's not. Okay. So to multiply two matrices A and B, once they're compatible, okay, we operate a row with a column. To generate a single element. Okay. So I'll show you one, just an isolated example, just to show you how this works in a bigger scenario. Okay. If this is a row, I'm going to use subscripts here, A11, A12. Okay. That is first row, first column, first row, second column. And I'm doing this as B11, B12. So the number of columns here, 1, 2 columns. Number of rows here, 1, 2 rows. Okay. So that's the requirement. Okay. 2 columns, 2 rows. The operation would remind you of what you probably did in the dot product of vectors. You're going to multiply these two, A11 times B11 plus A12 times B12. That is the row versus column operation. Okay. It's almost like your dot product of vectors where you multiply the components and add them together to get a number. Okay. Like vector dot product. And this is why we need the same number of columns as the same number of rows here, so that nothing is kind of standing out, waiting for something to operate on it. Okay. So let's do some examples and make sure that all of you are comfortable. So find A times B and B times A if possible. Okay, so let's start with very simple cases. So A equal to 1, 2, 3, 4. It's a 2 by 2 matrix, and B equal to 1, 2. Probably the most basic case. You have a 2 by 2 matrix acting on a 2 by 1 matrix or a vector. Okay. So the dimension of this is 2 by 2, and the dimension of this is 2 by 1. 2 rows, 1 column. Okay. The first thing is, are these two equal? Yes. And the thing I forgot to mention here is that your answer will be of this size always. Okay, AB, sorry about missing this part. AB will be of size M by P. So you know beforehand how big the matrix is going to be. Okay. So once those two middle things are the same, the product would be whatever was the number of rows in the first one times the number of columns in the second one. So in this case, we expect our result AB to be a 2 by 1 matrix. It's always nice to write out the dimensions and check and to kind of get an idea about what to expect in your answer. Okay, 2 by 1. So now that it's compatible, A times B would be, so the first entry would be 1 times 1 plus 2 times 2, okay, just like I did there. Okay, you are multiplying and adding them together. So it's 1 times 1 plus 2 times 2. Okay, that is going to be the first row, because it's a 2 by 1, right? The first row is here. And the second one would be 3 times 1 plus 4 times 2. So each row versus column generates one number. Okay, and this is equal to, don't forget your order of operations. This is 1 plus 4, 5, and this is 3 plus 8, 11. So in a geometric sense, what is happening is this matrix is changing this vector 1, 2 to a new position 5, 11. Okay, so that is the importance of linear algebra. When you apply this in applications, it transforms vectors into new positions. Okay. What about B times A? Is that possible? So to check B times A, just write it side by side, write its dimensions. B is 2 by 1, A is 2 by 2. These two are not equal. Okay. So it's not possible. It's a really weird operation because sometimes one of them is possible, the other one is not possible. Sometimes both of them are not possible. Okay, so it is not a commutative operation like you would expect. Because most of the math operations you have done so far, doesn't matter whether you go from left to right, right to left. Okay, it's all the same thing. Is that an alien? Okay, so note that in general, for two matrices A and B, okay, AB is not equal to BA. That is not a very common result in math, at least in lower level math. You expect, oh, 5 times 3 is same as 3 times 5. Okay. The closest you'll ever probably come to this is vector cross product. Even there is some relationship between those two. Here it's absolutely nothing that you can expect. Okay. One of these may not be possible, both may not be possible, both could be the same, I don't know. So let's do a couple of examples. Example 1. Forgot to pause and ask for questions. Any questions about this operation? I don't want to catch you on exam 4 or test 4 not knowing how to multiply two matrices. It's a very simple thing, but you should know how to do this. Okay. So let A equal to 1, 2, 3, 4, 5, 6, and B equal to 2, 1, 3, 2. So number of columns, number of rows. Okay. Find A times B and B times A if possible. So I'm slowly expanding the size of the matrix. Okay, I had just a column matrix or a vector in the second example, the example I did earlier. Now I've got a more generic case. Okay. So I'll do this and then I'll let you do the next one yourself. Let's make sure that At least one of this is possible. A is a 3x2 matrix, 3 rows and 2 columns. This is a 2x2 matrix. Those two are the same. Good. Okay. So the product AB is defined and will be of the size 3x2. That is a compatibility check. Right? Okay, so let's write those two matrices side by side. 1, 2, 3, 4, 5, 6. Sorry for picking the same numbers over and over. 2, 1, 3, 2. You expect 3 rows and 2 columns in your answer. Okay, so they better look that way and not some unexpected size or dimension. Okay. Again, for those of you who are still catching up on this, the first element would be 1 times 2 plus 2 times 3. That is the row versus column operation that is going to fill up each position. Okay. The second one would be 1 times 1 plus 2 times 2. We expect 2 columns, and there they are. That's the first column, second column. Keep doing this. We have 3 times 2 plus 4 times 3. You don't have to write all these details, okay? It's just because it's the first example. You can just mentally do it and write it down. And this one will be 3 times 1 plus 4 times 2. And the last one will be 5 times 2 plus 6 times 3. And the third row, second column would be 5 times 1 plus 6 times 2. All right, so let's do those calculations. You don't need a calculator for this, I hope. That's 2 plus 6, 8. 1 plus 4, 5. 6 plus 12 is 18. 3 plus 8 is 11. 10 plus 18 is 28. And 5 plus 12 is 17. So as expected, it's a 3x2, which means 3 rows and 2 columns. Okay. I don't have a huge problem if you get these numbers wrong because you forgot your additional multiplication. Okay. But if you write the wrong matrix or the wrong dimension for the matrix, that's when problems are bigger. Okay. So if you write this as a 2x2 matrix, that's a wrong matrix. Okay. Pretty forgiving towards numerical mistakes, could happen to anyone. Okay. What about B times A? Is that possible? So B is a 2x2 matrix. A is a 3x2 matrix. They are not equal, so don't even try. Okay. Okay. Any questions? If you don't have any questions, why don't you try this one? Example 2. That A equal to sine theta cosine theta. If you're a computer science, somebody who is working in computer graphics, okay, that's one of the most important matrices you would see there. Sine theta, cosine theta, negative sine theta. Find the matrix A square, which means find A times A. Okay. It's a 2 by 2 matrix, so there should be no surprises here. Can you try to do that? So just write it side by side and see what you will get if you multiply together. Once again, square matrices comes with its own privileges. Okay, you can always multiply two square matrices of the same size without being concerned about how many rows and columns they have. Okay, so it's a 2 by 2, 2 by 2. Answer will be 2 by 2. All right, so let's see what happens. So slowly multiply each row and column and write it into its respective position. Sine square theta plus cosine square theta. Okay. Something tells me that you know what that is. I don't know. Okay, so that's the first row, first column. The first row, second column would be sine theta times cosine theta minus cosine theta sine theta. Okay. It's obviously something, right? The second row, first column would be cosine sine minus sine cosine. And the second row, second column would be cosine square minus negative positive. Okay. Let me check your memory. What is sine square theta plus cosine square theta? 1. That's good. That's a 1. This one I'm not going to ask you. It's 0. Okay. And this is also 1. Don't know. Have you seen this matrix before? I told you that it was an important matrix. Okay. It's called the identity matrix because it kind of preserves the identity of whatever you're doing. Okay. But you might be thinking the identity of what? What is preserved here? So that's still a mystery. But at least you started with this matrix, okay, which tells you about some kind of a rotation by an angle theta. That's what computer graphics people do. They try to take images, they try to rotate it and see if they can restore it to the same position. Okay. So if you are able to achieve that, that is a good thing. Okay. If you are ending up with a different position, then probably not. So for obvious reasons, it's also called a rotation matrix. Okay. But we are not doing graphics here, so I won't go into that. Any questions on that one? So let's take advantage of this. So let A equal to 2, -3, 5, 4, let's say 1, 2, make it a 3 by 3 matrix here. So let A be this matrix, B equal to the 3 by 3 identity matrix. Okay. Find A times B and B times A if possible. And also, once you get these answers, just observe and tell me what you see there. Okay. So that might answer the question as to why this is called the identity matrix. So if you've never seen this before, okay, and if you're trying to unravel this mystery about why this matrix is so important, maybe this example will help you. So find the product A times B and B times A. Both are compatible. Okay. All right, so we are multiplying two 3 by 3 matrices. So the answer would be a 3 by 3. Okay, there is no other number here. If you're getting bizarre answers, it's okay. That's the whole point. So, people online, do you see something that is worth reporting, or what do you think?
Is the first one the transpose of
Just
it?
unmute and tell me what you get.
Is the first one the transpose of A?
Unless all of you are sleeping. Nobody wants to try their. Just unmute and it's okay. Even if you're wrong, that's fine. All right, anybody here? Get A? Did people online, did you get A? Can you at least confirm that by typing in the chat? Did you get the same matrix A or something else? Okay, good. At least you are there. Okay, so we're just doing a row versus column here. That's going to be the first row versus first column will give you 2. The second First row versus second column would give you -3, okay, because you're multiplying these two. And the first row versus the third column will give you 1. And the same process, okay, 5, 4, 2, 1, 2, 4. What about B times A? Will give you B. Did you try that or was that a guess? Oh, okay. That is comforting. You get A again, right? So B times A is also A. Yeah. If you did that and got this as the answer, I would be troubled. But yes, so if you do it the other way, okay, which means you keep that matrix here and do the same operation, you'll get the same matrix A. So 2, -3, 1, 5, 4, 2. In this case, it's compatible. Okay, there is no issue of compatibility here, and not only that, it's a miracle answer because both of them give the same answer. Even if I said in general it's not true, it's a very special case. Yeah, 1, 2, 4. People online, you said what you got? B times A. Did you get the same answer or?
Yeah, I got the same answer.
All right, good. So what can we conclude here? What do you think is the special thing here? Is it the matrix A or is it the matrix B? B, okay. A is some random matrix, I didn't care, right? So A times the identity matrix is always equal to the identity matrix times A equal to A. So this is a square matrix. What is the if thing here? If not the same size really, but if they are, what is the word that I kept using? Compatible for multiplication. Yeah. The number of columns here must be the same as the number of rows here. So if they're the same size, that's good. Okay, but that's a really extreme condition. Okay, if this has the same number of columns here times whatever, then that will be the same as A. Of course, then the I times A may not be defined. So if they're square, that is a good thing for peace of mind. Okay. So if this is equal to A whenever the multiplication is compatible. It goes without saying that if A is a non-square matrix, then one of these may not be possible. Okay, that is not our fault. But if they are possible, then it's always equal to the matrix that you multiplied with the identity matrix, okay, and it is commutative in this case. Any questions on that one? So it's a statement there to make carefully. You cannot say that the multiply any matrix with I, you get the same matrix if they're compatible. Okay. My last question to you is this, okay, from section 4.1. Suppose A is a m by n matrix. Question. Is A transpose and A transpose A always defined? If one of these or if both of them are defined, what will be the dimensions? This product is very important when you do least square. What is the dimensions? Least square straight line fitting for a set of data points. Okay, if you have a non-square situation, doing this A transpose and A transpose A is a very helpful multiplication. You probably would see it in a lot of applications. So, but this is a yes or no question. it's always a square matrix, no matter which way you do it, right? A transpose would be m by n, n by m. Okay, they are the same. So if you do A first and then A transpose, that's a m by m matrix. What about A transpose A? Is that possible? Yes, it is. Okay. A transpose A would be n by m, m by n. Okay. Once again, these are the same, so the answer would be n by n. In this case. It's the easiest and the most efficient way to get a square matrix out of a non-square set of data. Okay, when you do these straight line fitting between data points which are all over the place. It's a very useful and effective trick that a lot of people do in computations. But the question is, what is the immediate need for this? Why matrices? Other than for these fun computations, how does it fit into the linear algebra part of what we are doing? Okay. So earlier I wrote a system of two equations and two variables, which is a very easy thing to deal with. Okay. Let's just write a general situation: a11 x1 plus a12 x2 equal to b1, and a21 x1 plus a22 x2 equal to b2. So here the variables are x1 and x2. All the other things are numbers which we know. Okay. So x1, x2 are the variables which we are trying to find here. Okay. We use subscripts because at some point we run out of letters. Okay. So if this was a really big problem with 38 variables and say 43 equations, we don't want to keep on writing A, B, C, D, E. Okay. So that's why the subscripts are super efficient in terms of denoting these positions. So when you write 1, 1, that's the first row, first column, or the first equation, first position. Okay, this is the first equation, second position, second equation, first position, and so on. Okay, that's why the subscript notations are very popular with people who do coding. So Aij will mean ith equation, jth position. Very efficient in storing data. Okay, so when you say A2355, that means 23rd equation, 55th position. We can write that same system, okay, of 2 by 2, which might look like an overkill, in a matrix form as follows: A11, A12, A21, A22. Okay. So here the subscripts are making a lot more sense. First row, first column, first row, second column, second row, first column, second row, second column. Okay. Times your matrix or your vector of unknowns, which is your x1, x2, equal to the right hand side, which we know. Okay, that should come with a problem. So b1, b2. So if you understood the matrix multiplication that we just did, this should make sense. You have a11 x1 plus a12 x2 equal to b1, and a21 x1 plus a22 x2 equal to b2. Okay, so this is the same as what you did there. This is easier to manipulate, especially when the system is bigger. Okay. Easier to manipulate and solve. Well, it comes with some practice. When I first say it's easier, a lot of students give me that look, like, what do you mean? So with some practice, okay, dealing with these things are a lot more easier than dealing with the raw equations. That's why matrices are kind of convenient tools in linear algebra to solve systems of equations. Okay. So we'll do it tomorrow. So section 4.1 is done. So after your test tomorrow, you can sit down and do a whole lot of matrix addition, multiplication, all that stuff. Okay. So tomorrow we'll start 4.2 slowly. May not be able to reach too far, but if you have any questions for the test or something, please bring it in. Okay, I'll be more than happy to solve any lingering questions about the U function, delta function, so you can use it as a review session if you want to. All right, so I'll stop there and have a nice day.
Thank you.
Great.